Did we go over the residual standard deviation and the approximations, or cause it was like we read in the book.
Yeah, it was in the homework. I did not put it on the quiz.
I didn't understand it like
Not
100%, so it's
okay. I'll talk about it. I'm not planning on putting it on the final, but I'll talk about residual, what is it, residual standard deviation? It's kinda, maybe I'll just talk about it conceptually, and that will suffice, I hope. So the residual is the difference between the actual data point and what the line of best fit predicts we would have at that x value. So maybe the line of fit says for x equal to 3, we predict y will be 7 or something. And maybe the true value is that it's 9. Okay, so the residual is the difference between that 9 and the predicted value of 7. And all of the points in your data set will have some kind of residual. Okay, so when you take a standard deviation of that residual, it gives you an idea of the spread, or how different the residual, how different the actual points are from the predicted point. So if your residual standard deviation is small, that means the actual points do not vary, are not very different from our predicted points. If your residual standard deviation is huge, then that means the difference between the actual and the predicted is quite large. Okay, so it's kind of like a measure of how accurate your model is at predicting the values. Okay.
You said that's not on the test?
Yeah, I didn't put a question related to that on the exam. Do you want me to go back?
Or R squared, or
R squared,
deviation
on the
of
other
residuals?
hand, R squared I think is fair game. What is R squared?
1 minus x squared x y.
Okay, that's one way to do it. That's the approximation. The R squared, just take R and you square it. For linear regression, if you take R and you square it, you get R squared. For other forms of regression, that's not the case. Okay, but linear regression, the simplest form of regression, you take little r correlation, you square it, and you get R squared, big R squared. R squared is a measure of how accurate your model is also. It tells you how much of the variation in y is explained by the variation in x. I'll write that up on the board. So for linear regression, R squared is equal to R squared. Okay. Not for all regression. And R squared is the amount of variation x, or explained by general form is explained by the model. Okay, this first line only applies for linear regression. So you have a model, and it's trying to explain why your y's all have different values. Why does this house have 8 closets and this house only have 2? Well, the reason why this house has 8 closets is because there's 4 bedrooms, and this house only has 2 closets because there's only 1 bedroom. Okay?
But in a situation like that, how did you decide which was x and which was y?
It doesn't matter.
Oh, okay.
R
Because
squared's
you said
gonna be
one
the
is
same.
explained by the other. But it's the same to say that the other is explained by the first?
Yes.
Okay.
Okay. when we say explained by, we're not saying cause and effect. We're just saying that that kind of explains a relationship, I should say. Explains a relationship. A lot of times when you hear explain in English, it means cause and effect. But not necessarily in statistics, we just consider a relationship. Alright. Nobody has any questions on any of the tests? Yes.
Can you go over just when we have the tail value when we double it?
Yes.
Just because I feel like there's so many different ways.
Okay, so your best guide here is to read the table, okay? So at the table it will say the p-values given are for directional or for non-directional or something, okay? It doesn't say that on the t-table, but there's a picture and it only shows one tail in the picture, okay? So, so let's say you're doing a t-test, and the null hypothesis will always have an equal sign, alright? So it might be mu1 is equal to mu2, or conversely we can write mu1 minus mu2 equals 0. And then the alternative, if it has greater than or less than, means we have a directional test. And if we have a not equal sign, we have a non-directional test. Okay. In both of these cases, your test statistic is calculated the exact same way. Okay? Is equal to, you go through the calculations, you get your test statistic. Okay, if your test is non-directional, you take your test statistic, look it up in the t-table to get your tail area. Get the tail area, okay, and if it's non-directional, multiply tail area by 2. On the other hand, if it is directional, what do we want to do? We want to see if our data matches what our alternative says, okay? So if our alternative was that mu1 is greater than mu2, then what should our data say?
Well, whichever sample comes from population 1.
Yeah, so if this is our alternative, then our data should show that x bar 1 is greater than x bar 2, okay? And if our data doesn't show that, then that would indicate that the directionality of our data doesn't work. Okay, so check directionality. Okay, so if the alternative is that mu1 is greater than mu2, then the data should show x bar, or I guess y bar 1 is greater than y bar 2. Okay. And if it does, go through the test and take your tail area. Okay. Yes. Then test statistic, find the tail area, and that would equal your p-value. Leave your tail area, and that's your p-value. Okay. If it doesn't, then what do? We can stop there and say we have no evidence. Technically, you take your tail area and then subtract that from 1. And that would be your p-value. Just say no evidence. And then technically, your p-value would be 1 minus the tail area. Because the directionality is not there. Alright. Should I do for, maybe not the t-test, but let's say, okay, let's talk about maybe chi-square test for independence. Alright, chi-square test for independence means I have what kind of variables?
Categorical.
I've got 2 categorical variables, alright. Alright, so what are my 2 categorical variables that may be related? So we'll say gender, male versus female. And what is something that is related to gender, another categorical variable? Long hair versus short hair. Okay. Hair length. And we will just say long. So we'll say, I don't know, what do you call this? Long or short. So if it goes beyond a certain, like your shoulders, it will say that's long, and if it doesn't, we'll say it's short. Okay. So in this case, someone might say there is a relationship between long hair and short hair and gender. Probably is. Alright, so our hypotheses would be independent. And then the alternative would be more women have longer hair. Okay? So symbolically, what would we say?
Probability of
So probability of long hair given male would be equal to probability of long hair given female. Is that fair for independent? And then here we would say probability of long hair given male would be, now if we wanted directionality, we would say this, right? We'd say if we know that someone is male, the probability that this person, that he has long hair is less than if we knew this person was female. Okay, so we would do that for directionality. Okay. So how do we check directionality with our data? Yeah, so our data should show that P1, if we do the number of long-haired, proportion of long-haired males, should be less than P2, okay? The data should show P1 less than P2, okay? And then what do? We go through the problem. We get your chi-squared statistic. So you do observed minus expected, squared over expected. How many numbers will I be adding together for this?
however many boxes you have.
Okay, so how many boxes do I have?
I guess you have
Four.
I've got 4 boxes. Okay. And how many degrees of freedom?
One.
I've got 1 degree of freedom. Okay,
Yeah.
chi-square test for independence, number of rows minus 1 times number of columns minus 1. 1 degree of freedom. And then, if the directionality is met, I would look this up in the table. And if you read the chi-squared table carefully, it says the column headings are for non-directional alternatives. So for directional alternative, you would have to take that and divide by 2. So look up chi-squared statistic, and then divide column heading two. Yes.
For the null hypothesis and the other hypothesis, you can switch the L and M's and L and S and
Yes.
use the same thing, right?
Yes. Yes. Question. Is this a valid null hypothesis? Yes or no?
Isn't that what you just asked?
Well, he said, can you switch things? But I guess some switches yes, some switches no. So I'm asking, is this an okay switch?
I think no, because we're trying to determine if hair length is dependent given a certain gender. So the gender should be, right?
Okay. Well, so I'll say this is not valid. Alright. It's only valid if the proportion of male and females were exactly the same or something, okay? What about this?
I guess it is. Because it assumes you have to assume something about the female.
No, well, I don't know. But this one is valid, okay? This says if somebody has long hair or somebody has short hair, our prediction of whether or not this person is male or not doesn't matter. Length of hair.
So why isn't the first one valid?
Because this one says if somebody has long hair, our prediction of okay, let me change this around here, okay? So this feels like it could be valid because we're accustomed to seeing 50% male and 50% female. Okay. Alright. But let's say we went to is there a school that's mostly one gender but not okay,
Vassar
so
College.
okay, Vassar College. It's like mostly female, right? So let's say we go to Vassar College and then I say, okay, I picked a random student from Vassar College. This person has long hair. Do you predict that that person has an equal chance of being male or female? No, because inherently in the population, the probability of male and female are not equal. Okay? Now if I I say, I picked someone from Vassar College, and this person has short hair. Would your prediction of male or female change? Probably. Okay, so whereas before behind the door I said somebody from Vassar College has long hair, you'd probably say, oh, 90% chance of being female. Okay, now I say this person, and 10% chance of being male. I say, oh, the person behind the door has short hair. I say, oh, maybe 20% chance of being male, or something. I don't know. Whatever. I don't know what the demographics of Vassar College is. Mostly female. Whereas the school I went to for undergrad was mostly male.
So where'd you go, MIT?
I went to Kettering University, engineering school. Used to be run by GM. That was where they trained all of their engineers. So definitely lots of guys. Hey, stories go. Yes.
So the second valid one that you wrote does not mean the same null hypothesis as the other one we wrote, does it?
These two are equivalent in nature.
Okay.
These two are basically saying length of hair and gender are independent.
Okay.
Okay? Because if this is true, then this must also be true. Okay. So if A is independent of B, then B it must be independent of A. I know these probability rules sometimes they feel funny. Okay. Yes.
So wasn't there another test that we had to double it or halve it or something?
Yeah. ANOVA. Oh, no, not ANOVA. ANOVA is always going to be non-directional, almost always. Wilcoxon-Mann-Whitney. Okay. Well, and there's several chi-square tests, right? Chi-square test for goodness of fit. Can chi-square goodness of fit be directional?
Yes.
Yes? Okay. No?
Yeah,
Yes.
I can.
Okay. So what must be the case for it to be directional for chi-square goodness of fit? The answer is yes, it can be directional.
Only two probabilities.
Yeah, only two categories. So, chi-square goodness of fit, if you have only two categories, so basically, let's say the categories are yes and no, it can be directional. So let's say, so your model says yes is 70% and the no's are 30%. This is your model. And somebody says, no, that model is wrong. I think you have too many what? Too
Yes.
many yeses or too many no's or whatever, okay? So, according to our model, basically the probability of yes, I should say piece of y is equal to 0.70, okay? And that would imply that the probability of no is 30%. And then the alternative, if we said we have too many yeses, then probability of yes must be less than 70% or something, whatever. Your model is wrong because it's predicting too many yeses. Okay, so then we'll go through our thing and we divide by 2. What should the data show though to check directionality?
Yes.
I'm sorry?
Should show less yeses.
the data must show that, so you're gonna get basically a p hat for the yes and a p hat for the no. And your p hat for the yes should be less than 70%, okay? So let's say your data was 80 yes, 20 no. Okay. Is there directionality met? Yes. You have another hour. Or 50 minutes.
You can't do anything with them.
So this one, directionality is not met, okay? This p hat would be 0.8. That is not less than 0.7. No evidence to support it. Okay, let's try this out though. Okay. So let's say we switch this around. Okay, our directionality is now met if we did this. What's my chi-squared? How do I get my chi-squared statistic?
Have the column value.
Is that?
Have the column value.
So I do observed minus expected, right? So what are my expected values? So I've observed a total of 100 answers. So under our model, I would expect 100 times 0.7. I expect 70 yeses and 30 nos. Okay? So then my chi-squared statistic would be observed minus expected squared over expected. Observed minus expected squared over expected. So I get 100 over 70 plus 100 over 30. Don't know what that is. We have chi-squared statistic of 4.762. Okay. Now I look this up. And then, because it's directional, we divide tail area by 2. Did I do that too quickly, or that's okay? Yes.
Did you say the material from the first midterm will be on this test?
I have a few miscellaneous grab bag questions from, I guess before the midterm, general statistics related questions. Maybe 3 questions or something.
And
What do we have
how
to do
much
on
paper,
that?
sorry,
Sorry, go ahead.
how much paper can we use as notes on the test?
You get 1 full sheet of notes, front and back.
Do we we have to solve anything though? So first part.
No.
Oh.
No calculations.
What about R? Is there anything?
No R questions.
What was
Just
the
kidding.
second to last question? What did you
Do you,
ask?
are there any like calculation math solving questions from the first half of the course?
So you say from the midterm, right? It's multiple choice or no?
Yeah, it's all multiple choice.
Okay.
Okay. Feeling good?
Yeah.
Alright. Okay. Well, if that's it, you guys may go. I have to stick around.
How many questions are there?
Between 50 and 60.